Thank you, Jaya, for joining me today. I'm speaking with Jaya Savitsky, who is one of 18 authors of a paper, a recent paper, that put a date, put a time frame to our emergence from the Holocene era into the Anthropocene era. Am I correct?
Correct. Although the date is still not locked in a legal sense, it says mid 20th century.
Okay.
And 1950 is how we mathematically use the values from before and after.
Okay. Okay. So
Yeah.
mid 20th century, and we'll use
Correct.
1950 as a pretty good estimate of what mid-century means.
Yes. Yeah.
First off, what reception has the paper gotten in terms of the press, in terms of the public? What feedback have you gotten about it?
Well, I don't know the answer to that either. I haven't been checking. So, it's had, I don't know, close to 1,000 reads already. So I don't know whether that's even impressive or not.
Okay.
It hasn't come out in print yet. So it's a little premature, but there is a web, you can download a web version of the paper.
Is it going to be peer reviewed?
No, it's already peer reviewed. It's just, it comes out first electronically and then it'll come out as one of the Nature magazine articles in print.
Let me ask you the point. What did your group hope to achieve in actually putting a date or an approximate date to our emergence into the Anthropocene era being, correct me if I'm wrong, the era in which humanity has become the dominant force of nature and we are
Correct.
controlling the environment?
Correct. So there's always a lead up, and in the paper we mentioned that humans have been a geological force for the last 300 years. So even though it's been a geological force, in other words, before then, the human footprint was of regional extent. It wasn't a planetary extent. But around the mid-century, the 20th century, the amount of the footprint of humans is such that it's changed most of the Earth's systems. So you can see it in the oceans, you can see it in the atmosphere, you can see it in the terrestrial system, the ice system, the cryosphere, and most of the Earth's systems have a determined human presence of global magnitude, and that would date from around then. And so we compared that post-1950 to the Holocene, which dates back 11,700 years. And that has already been broken up into three ages. And these ages, they reflect natural changes in the Earth's system. Planetary motion is the big one, the Milankovitch cycles.
So the Milankovitch cycles, as I understand it, are three. One of them is the inclination of the Earth's axis. It wobbles a little bit.
Yes.
The other one is that it's called precession, like a top. When a top slows down, it starts to, the axis of rotation starts to move in a circle. And the third, if I understand, is that the path of the Earth around the sun is an ellipse, which stretches and shrinks.
Yes.
Okay. And those three, now let me see if I can go further. The wobbling on the axis is an 11,000 year cycle, approximately. The precession is approximately a 40,000 year cycle.
Correct.
And the flexing of the Earth's orbit around the sun is approximately a 100-year cycle. So it's as if you were taking the biorhythms of the Earth and plotting them against one another and getting parts where all three are up or all three are down or they're countering one another. And so what you said was we should be in a cooling period now, by the sum of these three Milankovitch cycles. But instead of experiencing cooling, we are experiencing 1+ degrees of heating, warming
Yes,
above what would have been cooling. So can you
that's correct.
give an approximate number to what that background cooling would have been if humans had not been interfering?
Thermal equilibrium for the last 10,000 years is shown as 0 watts per meter squared. Ice Age is around -6. For the past million years, the natural cycle has oscillated between warm periods and ice ages. Milankovitch cycles initiate these natural changes. Changes in the distribution of sunlight alter seasons, greenhouse gas concentration, ice cover, and ocean temperature. Lately, natural cycle produces a warm period about every 100,000 years. We came out of the last ice age 10,000 years ago. In the natural cycle, Earth should gradually cool, descending ultimately into another ice age thousands of years from now. Instead, we are warming. Increased greenhouse gas concentrations have increased climate forcing. Total positive forcing is estimated around 3.6 watts per meter squared above thermal equilibrium, higher than it has been for millions of years. The climate system has left the path of natural cycle. We are warming, and the warming is accelerating.
We should be cooling now, but we're not cooling now. We should still be part of that cooling system. And that relates to sort of the Milankovitch effect. So in that we're over a degree already. That's a degree on top of, we've added even more energy to the system. And this energy that we add, it's largely from fossil fuels. 80% of our energy consumption is fossil fuel based. The size of the human footprint is not that old.
But the
from a global perspective.
The takeaway to our audience is that we are clearly in the Anthropocene age.
Correct.
Okay. Now I want to.
And this is from a geological perspective. The Anthropocene Working Group, the geological side will be determined from looking at the various sites around the world to what represents a marking horizon in the sediments that have accumulated since a particular period of time. So if we were to finalize the Anthropocene as 1950 as an example, everything that's even not related to humans, but everything after 1950 would become part of the Anthropocene. So that would mean that if there was a volcanic eruption, even though that has nothing to do with humans, that still would be part of the Anthropocene. So the Anthropocene is like a marker. And you can see it in the rock record. And the paper itself is not really focused on the geological evidence per se, rather than the driving factors. What caused humans to have such a footprint on the Earth and the Earth system. We have historians, we have social scientists, we have geological science, and all of these various authors contribute to their expertise, because I really think it's pretty difficult to have scientific command of all these different disciplines. And so unless you put together a really interdisciplinary team, you're limited. You enter the subject matter limited. And because it's the history of humanity, and it needed a lot of experts on the paper to get there. Someone would bring in changes in the geochemical cycles. Well, that's not my field. And what they contributed was very valuable. How, we were these different elements, we're now the controlling factor on most of these chalcophyll elements and platinum elements and other cycles. So the ecosystem scientists would bring in the controls that we now have in the nitrogen cycle and things like that. And so it's a huge paper in its breadth. And all we wanted to do was to make sure that when we used a value, that the quantitative value we used was the latest and best value, because as we get more and more details in science involved, numbers can change. And we wanted to have, well, what's the state of the art today? And the state of the art depends on these experts that came in.
Okay. Now, would you discuss, lay out as many as you can in a list form, and then we'll go into a few of them, the stressors, the elements, the dimensions in which humanity has become the controlling factor in this variety of parts of this overall Earth system? What parts did you examine?
You know, the parts that I suppose that ran through our analysis of the Holocene and into the Anthropocene, because certain values like plastic, it wasn't present in the Holocene, so you can't do an analysis on that. But when we were looking at the last, let's say, 12,000 years and more, we looked at invasive species as an example. You know, when did that become global? And was it one species or 100 species or 1,000 species? And, you know, when did that happen? Another one would have been extinctions. Some extinctions that have occurred in the past were related to these Milankovitch cycles, these natural cycles in the system. But some of them were related to humans, even in the Holocene. So we would point that out. When did croplands, you know, become big on the planet rather than just regional? It's important because these croplands yield a lot of soil erosion. That soil erosion provides the sediment along with the carbon that is then flooded down to deltas and coastal systems and marine systems. And that becomes part of the stratigraphic record. So we paid attention to that. Deforestation was another one that has been traced over a long period of time, and many other things, but we were particularly tracing over that longer period of time, we were tracing humans themselves. What was the population? What was their sort of annual energy consumption of an individual human, you know, 12,000 years ago compared to today? What was the productivity of the humans? Because, you know, most of the energy that was being consumed by these humans until a few hundred years ago, it was mostly to survive. It was survival energy. It was to find fodder for their animals. And so they were, or themselves, it was not what we have today. We have so much spare capacity and energy that the productivity that then leads to the footprint magnifying, like dams and you know, mega cities and things like that, that wouldn't be possible if most of the energy was going to survival mode. So when we were tracing, and we were tracing a lot of things that we thought it'd be nice to go back as far as we can, but many of them don't go back that far. So cement production is an example where the Portland cement recipe was invented, you know, around, I don't know, 1840 or something like that. And it had a very low global footprint, cement making concrete, by 1950. But 1950 and since, it's just shot up many orders of magnitude. I mean, there was some cement used by the Romans and things like that, but it was not quite what we call industrial scale cement use.
No, but the formula, you mentioned the formula. So I thought the Romans actually invented cement. They cooked up the formula, although it was probably...
Well, it wasn't Portland cement. The Portland cement was a formula that allowed for industrial industrialization, industrial scale production.
Yeah.
It was because of that formula.
Yeah.
And what the Romans did, and I'm not an expert in this, it was used in a very local environment, but it wasn't used that we can see it as a signal around the planet.
Yeah.
And the field of anthropology and archaeology and all of that, you know, they're interested in when something first took place. They're not interested when whatever that something is started to change how the Earth system operated.
Your paper in particular looks at that, how
Yes,
that those things started to change how the Earth system operated.
correct.
Would you say most, some, all of the dimensions that you looked at are negative in their impact on the ecology of the Earth? Have we had any benefit in our, of course, benefit is depends upon the eye of the beholder, you know. Oh yeah, we got a lot more iPods now. You can say that's a benefit, but
We that's not our paper to make judgment. If you're asking me personally, I think what we found out is that we are so far away from even 1950 in 2020. It's just amazing what our footprint is. And so although when we look at it, one can say to oneself or to each other, well, you know, is megacities, is that a good thing or bad thing? You know, megacity is a city that has 10 million plus people. In terms of scale, it caused the largest migration in terms of numbers ever on the planet. These megacities, well, is that a positive thing or negative thing? And you could argue about that. Well, you say, well, where are they? Well, they're mostly in the coastal zone. Okay, is that a positive thing or negative thing? Well, this heavy population needs drinking water. So even though they often form on deltas, they don't often get their water supply from these big rivers that flow through into the deltas. They get it from below ground. Well, if they get it from below ground, they're pumping up this water, they're subsiding the land. So is that a good thing or bad thing? Well, I think it's a very bad thing. Sea levels going up, let's say it's 3.1, 3.2, 3.3 millimeters per year today. You're sinking land, well, 10, 20, 100, 200, 300 millimeters per year. So the amount of sinking that's going on around the world in coastal zones is being affected by these megacities. So if you, depending on how you define what's a good thing and a bad thing, it's a bad thing. But if these people weren't having a hard time making a living and they were having a hard time getting food supplies and things like that, then megacities are a good thing. So I don't know.
yeah, no, I understand.
Our job is not to define it.
No, I understand, and I will emphasize the disclaimer that you made that you're expressing your personal opinions and not the opinions of the paper or this group of scientists.
Yeah, we didn't put any opinions in the paper. Yeah.
But from my perspective, I am constantly trying to issue a wake-up call to humanity that we'd better take our foot off of the neck of Mother Nature, or she's going to fight back in no uncertain terms. And a lot of people point to some of the things going on as Mother Nature fighting back. Now, Mother Nature is an anthropomorphized notion, but I guess my point is, if you judge the survival of life on Earth, of which humanity is a part, and the survival of humanity as a species, if you view those as the goods, then how destructive have we been to our own chances of survival and the overall chances of survival of life through the weight of our mega footprint?
Well, I think people have a hard problems when we say that it's warmed up 0.9 degrees, 0.9 degrees since 1950. They don't think that's very much degrees centigrade. They just don't think that's very much. But what they don't understand is that 22 times that is the energy that's being soaked up by the oceans. The oceans really are accumulating the energy. You can't accumulate much energy in the atmosphere. So you shouldn't expect much what people call global warming, but scientists don't think of global warming as what's in the atmosphere. They think of, mostly what's in the oceans. And so I think that there really is a problem in how we communicate the scale of things. And when we're dealing with a water planet, 70% of our water or Earth's surface is as oceans. And if you're not an oceanographer, you have little concept of how humans are changing the planet. For instance, the pH in the paper, we talk about how the pH of the oceans is changing. And it's changing because the oceans are soaking up all the CO2. Yes, the CO2 in the atmosphere is going up, but it's largely being impacted by the CO2 absorption of the ocean. But so what if it's becoming a little bit more acidic? That has, the average citizen has little they can grab onto to understand what that tiny change means.
That's my job. And I'm asking you to help me in that job, because that tiny change in the pH, which is the acid-alkaline balance, again, translating the technical term, although it's a common technical term, when we acidify the oceans, even slightly, those ocean creatures that depend upon a particular range of acidity, alkalinity for the formation of their exoskeletons, their shells, their larvae can no longer create strong enough shells to survive. And you've got this problem in the oyster industry, for instance. So the oyster fishermen are encountering the fact that there's less of the breeding in the wild, and there have to be more and more breeding of oyster larval form in captivity. And then if you put them out in the wild, then the acidity of the ocean can eat away at the shell. Basically, we are, in my perspective, we are sawing off the limb of the tree that we're sitting on. We are cutting.
And what we made clear in the paper is that, greenhouse gases is another of the topics that we think the public don't quite understand. Like greenhouse gases, the largest greenhouse gas is water vapor. And so what has humanity's use of fossil fuels, how has that changed the water vapor? Well, that's just a concept that's really hard to convey. Behind water vapor is clouds, and that plays a very important role. And then comes CO2. Mm-hmm. So now the water vapor and the clouds, they're because of the CO2. I mean, the feedback it's like a huge magnifier. 10, 20 times is the effect of these gases in our atmosphere. And they're starting to have even really large changes on water vapor and cloud cover. But it's CO2 that will last 100,000 years in the atmosphere, no matter what we do. If we stop CO2 consumption tomorrow, that's still up in the sky. That's why we're so sure that the Anthropocene has begun in 1950. We've done it already. we're not waiting for anything. We're here in this new world. It's a different world. And 100,000 years later, with no addition, that's when you finally get back to the natural cycles, if you don't then make other changes along the way. And people, they feel attached to certain things. Like, for instance, I hear a lot about methane. Well, methane's a very strong greenhouse gas. It's even stronger than CO2. It's just there's less of it as a forcing factor.
Yeah.
But if you change methane and you said, well, listen, we can't control CO2, but we can control methane. Well, that's not really going to change global warming. So that's a concept that's really hard to convey. When we make a change, is this a change that's so reactive? If we then changed our minds and we did something new, we all would be well? Well, that's our point. Our point is, and it's not doom and gloom, but our point is we're really in a pickle when it comes to things like our fossil fuel consumption and CO2. It's a dangerous, dangerous world we live in.